Welcome back. In the last episode, we learned how pressure changes can affect your instruments, your altitude, and your performance in flight. Now it's time to take it one step further. In this video, we're talking about density, what it is, how it affects your aircraft, and why pilots pay close attention to something they can't even see. So, what exactly is air density? It's the amount of air molecules packed into a given space. Think of it as the thickness of the air. The denser the air, the more oxygen, the more lift, and the better engine performance. Less dense air. Less of all that. Density matters. Air density depends on three main factors: pressure, temperature, and humidity. When pressure is high, air molecules are compressed, density increases. When pressure is low, the air spreads out, density decreases. That's the first key relationship you need to understand. Next is temperature. Warm air expands and becomes less dense. Cold air contracts, making it denser. This means your aircraft will perform better on a cold day than on a hot one. That's why performance charts are always temperature dependent. The third factor is humidity. Moist air is actually less dense than dry air. Why? Because water vapor molecules are lighter than nitrogen and oxygen. So ironically, on a hot, humid day, the air is lighter and your aircraft works harder to fly. Let's pull these together. High pressure, low temperature, and low humidity mean dense air. Great for takeoff, climb, and engine efficiency. Low pressure, high temperature, and high humidity mean thin air, less lift, more drag, and longer takeoff rolls. And this brings us to a key concept: density altitude. It's the altitude the aircraft feels like it's flying at, based on how dense the air is. The higher the density altitude, the worse your performance, even if you're physically at sea level. Let's say you're flying from a hot airport at 1,500 feet. Because of high temperature and humidity, the density altitude could be over 4,000 feet. That means your engine, wings, and propeller are all performing as if you were already at 4,000 feet. That's a big deal. You'll see density altitude discussed in pilot weather briefings, POH performance charts, and even ATIS broadcasts at high elevation airports. Pilots must calculate it before every takeoff, especially in warm weather or at airports above 3,000 feet. So how do you calculate it? Most flight computers or apps do it for you automatically, but here's the basic idea: take the pressure altitude, adjust it for temperature, and factor in humidity. The result is your density altitude, the real performance level. Let's go deeper. Higher density altitude affects engine performance because the engine receives less oxygen per volume of air. That means less power, slower acceleration, and reduced climb rate. Turbocharged engines are more resistant, but not immune. It also affects lift. Remember, wings generate lift based on the amount of air flowing over them. With fewer air molecules, there's less lift. You'll need more speed and more runway just to get airborne, and climb performance will be sluggish. Propeller performance drops too. A propeller is like a rotating wing. Thin air reduces its ability to bite into the air and produce thrust. That's why on high-density altitude days, every aspect of takeoff suffers, from roll to rotation to climb. This is critical at high-elevation airports, especially in mountainous regions like Denver or Quito. Add high temperatures, and density altitude skyrockets. If you're not careful, you might exceed the available runway before reaching safe flying speed. That's why aircraft performance charts always include tables or graphs for density altitude. These show takeoff distance, rate of climb, landing distance, and help you decide if you can safely operate under those conditions. Know your numbers before you go. Let's look at an example. A plane at sea level on a standard day might take off in 800 feet. But at 6,000 feet elevation on a hot day, that same plane could need over 2,000 feet to lift off and climb at half the usual rate. That's not just theory, it's reality. What about during cruise? Density still matters. At high altitudes, even with reduced air density, true airspeed increases, but engine efficiency drops. Pilots must balance power settings, fuel burn, and climb profiles with density in mind. And on approach and landing? Thin air means higher true airspeeds. Your ground speed is higher, which affects your timing and landing distance. You might float farther, land longer, or have less stopping room, especially with a tailwind. Aircraft performance doesn't just change slightly, it can change dramatically with density altitude. That's why it's part of every flight planning session. Ignoring it can lead to poor performance, aborted takeoffs, or worse, accidents. Thankfully, there are tools to help. Most flight planning apps let you input temperature, pressure, and field elevation to get real-time density, altitude, and performance estimates. Many also warn you if conditions exceed aircraft limits. Always compare the forecast temperature with your POH limits. If it's hotter than the performance chart allows, delay departure, reduce weight, or use a longer runway. Better to wait an hour than take off under marginal conditions. Remember, high-density altitude means you'll need more runway, more speed, and more skill. Think ahead. Trim properly. Use correct flap settings. Watch your rotation speed. And give yourself extra space, just in case. Even gliders and helicopters feel the effects. A hot day means less lift for wings, rotors, and engines alike. Helicopters especially struggle at high-density altitudes, hovering becomes harder, and vertical climb may be impossible at max weight. Another important concept is service ceiling, the altitude at which your aircraft can no longer maintain a specified rate of climb. High-density altitude reduces your service ceiling, which limits how high and how fast you can fly safely. For light aircraft, this could mean you're unable to reach cruise altitude or clear terrain. For heavy aircraft, it affects dispatch planning and fuel efficiency. Know your aircraft's limits and never push past them. Humidity plays a subtle role. Pilots sometimes underestimate how much moisture in the air can hurt performance. If it's a humid day, factor that in even if the temp isn't extreme. Every bit of moisture takes up space that oxygen could use. So, what are the pilot's takeaways? Always check density altitude before takeoff. Use performance charts every time. Watch for signs of poor climb performance. Don't overload the aircraft. When in doubt, delay, divert, or reduce load. Understanding density altitude isn't just academic, it's practical. It's the difference between making it off the runway smoothly or running out of tarmac. Between a smooth climb or one that drags for miles. Between a safe flight and an incident. If you're flying in the mountains or high deserts, pay extra attention. The combination of elevation, heat, and load can change performance drastically. Review airport charts, density warnings, and obstacle clearance notes in advance. One last reminder, density altitude affects everything. Engine power, lift, drag, climb rate, acceleration, takeoff roll, landing distance. You can't see it, but you can absolutely plan for it. Now that you understand density, you're ready for the next step in meteorology. In our next lesson, we'll explore pressure systems, how high and low pressure areas shape weather patterns, wind, turbulence, and more. We'll connect everything you've learned, pressure, temperature, and now density, with real-world weather systems. Get ready to meet highs, lows, fronts, and everything in between. See you in Meteorology number 05, Pressure Systems, Part 1.